Thank you.
Okay, our next talk will be by Micah Schaible from the University of Virginia. Micah is going to speak about hydrogen implantation in lunar soil, the role of solar wind in OH bond formation on the lunar surface. Okay, take it away.
So thanks for having me here today. Thanks for everyone for tuning in. Today I want to talk about the process of hydrogen implantation into the lunar soil and specifically into silicate minerals. Let me see if I can get this to advance here.
If you click on the first slide, then you should be able to use your keyboard. If not, you can use the arrow keys at the bottom of the slide.
It's just moving it around. Okay.
Yeah, try your keyboard keys.
It's scrolling it. Is it scrolling it for you?
The arrow keys, otherwise you have to scroll, but the arrow key at the bottom left of your slide, that'll do it easily.
So the basic theory is that the solar wind ions, they implant themselves into the lunar soil, breaking bonds between the silicon and the oxygen atoms. And then the implanted hydrogen can subsequently bond with the oxygen. And this was posited as the hypothesis to explain the 3-micron band absorption seen in the 2009 measurements. Some experimental work has been done on this already. Burke et al. In 2011 did experiments on terrestrial thin sections using ultra-high vacuum and irradiating the minerals with H2+ and H+ ions. And they set an upper limit of 0.5% absorption depth due to the implantation. Ichimura et al. Subsequently did experiments on plagioclase powders and lunar soils at a higher vacuum and after exposure to air, but they saw up to a 5% increase in the band depth. So because of these conflicting results, we wanted to do a few more measurements on this and try and really determine the effect of hydrogen implantation into silicate minerals. So that we constructed the chamber here at the University of Virginia. It is a cryopumped UHV vacuum chamber capable of 10 to the -9 pressure with a cryogenic sample holder, and we can do either reflectance or transmittance spectroscopy. Our ion accelerator is mass analyzed so that we can irradiate the samples with just H+ as opposed to H2+ ions. And one key feature is a pre-chamber, which allows us to bake our samples first and then directly transfer them to the sample holder without any air exposure. So the experimental setup was done as seen here using transmission spectroscopy. The irradiations were done at room temperature using 2 to 5 keV hydrogen and helium ions at a base pressure of 10 to the -9 torr. And the samples that we used were SiO2 grown on a silicate wafer to a thickness of 0.2 microns, and olivine, which was ground to a final thickness of around 150 microns. So what we saw after we irradiated the minerals with the H+ is there's a clear increase in the 3-micron band region for both the silicates and the olivines. Important note is that the olivine had a residual OH signal after the bakeout, but the H+ implantation still produced a clear increase in the 3-micron band. To make sure that the irradiation was indeed due to the implanted hydrogen, we checked our setup by irradiating the minerals with 4 keV helium as well. What we saw is that the structural changes due to radiation damage in the minerals produced no significant change in the 3-micron band region. It's important to note that these spectra here have actually been offset somewhat to show them more distinctly, but both of them, without that offset, are almost a complete overlay, one on the other. We also wanted to check if there was any significant change in the band structure or the band height after air exposure. So we took that helium irradiated sample and then exposed it to first H2 gas at a pressure of 1 torr for 24 hours and took a spectra, and then subsequently air at atmospheric pressure for about 4 hours and took another spectra. After both exposures, we saw no significant increase in the 3-micron band region. However, taking that same sample and then irradiating it with hydrogen, we do see this increase in the OH band area. So as we irradiated our sample to higher and higher fluences from 0 to a maximum of 2 times 10 to the 17 hydrogen ions per centimeter squared, we see an increase in the band area with increasing fluence, but no significant changes in either the band width or the general shape of the band area. So this tells us, or helps tell us, that the implanted hydrogen is forming a more or less spectrum of OH bonds in the mineral. One of the questions that's been asked since the original measurements of the lunar surface was whether or not the hydrogen implantation could form H2O molecules in addition to OH bonds. And to check this, we cooled our samples down to cryogenic temperatures. In the bottom left here, you can see another olivine sample that has a much higher original content of hydrogen or OH in the original thin section, and you can see that on cooling to cryogenic temperatures, there's a clear change in the band structure of that 3-micron band due to OH. Whereas for the implanted San Carlos olivine, we see no significant changes as we cool down to cryogenic temperatures. So this tells us that we seem to be forming only OH, and there's no significant amount of H2O molecules formed due to the hydrogen implantation. So as we implant our materials with the hydrogen, we see that there's a general drop-off in the increase in band area, and we see a plateau start at about 2 times 10 to the 17 hydrogen molecules per centimeter squared. At this point, the increase in band area starts to level off. We see similar increases for both 2 kV and 5 kV implanted SiO2, as well as the olivine and another mineral, albite. So after we determined the increase in band area, we wanted to calculate an increase in column density due to this hydrogen implantation. We did this by subtracting the irradiated absorbance from a pristine or unirradiated absorbance spectra, and then integrating that absorbance over the entire bandwidth to determine a band area. We then converted that band area to column density, and we see that for 2 and 5 kV implanted silicon, we get an increase of about 2 times 10 to the 16 OH molecules per centimeter squared. Where for the olivine and albite, we see a slightly higher increase of about 3 times 10 to the 16 OH per centimeter squared. It's important to note here that the integrated molar absorption coefficients that we use to calculate our column density were taken from the literature and were found using minerals that had not been irradiated. Now, it's possible that these coefficients could change for irradiated minerals, but at this moment, this is the best that we have to work with.
Micah, you have 3 minutes right now.
Taking that column density, we can find the percent of implanted hydrogen that is converted into an OH. And we see that initially about 60% of the hydrogen is converted to SiOH bonds, or OH in some form. And at saturation, there's about only 10% of those molecules have been converted to SiOH bonds. So of course, the lunar soil is a powdered regolith, and our measurements were done on slabs of mineral. So we wanted to be able to convert our measurements to some form of something that we can compare to the powdered regolith. And to do this, we assumed that regolith is formed of particles of average size t, and they're implanted to a depth t with hydrogen. And then using our measured column density for olivine, we can convert to an equivalent column density of a powdered regolith. Then using a correlation between our measured column density and the band depth of our measurements, we find that for a powdered regolith of olivine, we would find a band depth increase of about 2.6% in reflectance. Now, this is still below the in situ measurements from the moon and the Ichimura experiments. So in conclusion, we see that the irradiation of silicate minerals with hydrogen doesn't produce an increase in SiOH, or a 3-micron band absorption, while irradiation with inert ions, such as helium, produces no changes in that SiOH band. We saw no evidence for molecular water formation and an eventual plateau starting at about 2 × 10⁻17 hydrogen molecules per centimeter squared, at which point the OH starts to level off. That's it.
So much. I appreciate that. We have a question already from John Keller. Okay, so he says, 5 keV is fairly energetic compared to solar wind. Did you attempt 1 keV measurements?
At this time, we weren't able to complete the 1 keV measurements due to a lack in beam current. Our measurements were irradiating the samples with about 2 × 10⁻12 H+ per centimeter squared per second. So the irradiation times were already on the order of 24 hours. As we drop down in energy, that flux of hydrogen decreases, and at this moment we weren't prepared to sit there for multiple days irradiating the samples. But we do hope to improve our beam currents in the future and do irradiations at 1 keV.
Okay, great.
I should note that, go ahead.
Oh, no, please finish.
We did do irradiations at 2 keV, which is more similar to the solar wind energies. And we didn't see any major qualitative differences in the increase, although for that 2 keV measurement.
Okay, great. And we'll take one more talk. Shuai Li says, sorry for missing part of your talk. Do you have any experiments to show that as temperature goes high, the OH bond will be broken?
We didn't do temperature measurements that show that. I think Tom Orlando's group and Michael Poston, they do measurements that look at breaking that OH bond in minerals such as albite and lunar soil.
Okay, wonderful. Well, thanks so much.